Alright, so in this video, we'll be looking at sort of a summary of the reactivity for different EAS reactions, right? We looked at the ortho, meta, para positions, how to kind of work with that nomenclature in the last video. So now let's see where that actually comes into play, and that's going to be with directing groups, right? We have our activating groups and our deactivating groups. So before we get into sort of the logic as to why you would have a meta director versus an ortho or para director, let's identify which exactly those groups are, right? What our electron withdrawing groups and our electron donating groups are going to be. So if we sort of create a chart, right, let's start off with our strongly deactivating groups, or in other words, these are going to be our meta directors. So if we draw our benzene, the strongest deactivating group that you're going to come across is going to be your NO2. So you need to know this, again, when we're doing different synthesis problems, something we'll also do in this video, but you need to know that this NO2 is highly, highly deactivating. So now, what comes next? Well, another deactivating group, though not as strong as our NO2, is going to be the SO3H. So let me redraw this. So we have this SO3H, which again, we can attain this group through sulfonation. And so this is going to be another deactivating group. We also have generic sort of carbonyl, right? If you have a kind of a ketone here, if you have our benzene ring, and we have this carbon double bonded to an oxygen, and we have some R group, this here is going to be another deactivating group. So these here are examples of the groups that are strongly deactivating. So these are strongly deactivating groups, or in other words, these are going to be our meta directors. That means if we have this, any one of these substituents on a benzene and we undergo another EAS reaction, well, that electrophile is then going to only attach to our meta position. Again, meta relative to this substituent. So we wouldn't have any ortho or para products, right? We wouldn't have a substituent attached to our ortho or para positions. We would only have products contain where the next substituent would attack this meta position, and that is sort of the concept here with these different directing groups based on adding or removing different substituents at different points along this synthesis. We can kind of influence the locations of our substituents. We can produce very precise products here. So here we have these strongly deactivating meta directors, right? So now we can move on to the halogens, right? Our halogens are going to be things that are slightly deactivating. They're not strongly deactivating, but they are slightly deactivating. We can generically refer to all of our halogens with the letter X. And so these halogens, again, are things like our fluorine, iodine, bromine, chlorine. And so these are going to be slightly deactivating. And while they are slightly deactivating, these are actually not going to be meta-directors. Again, the actual chemistry as to why something is an ortho, meta, or para-director is going to come in a future video. But know that even though these are slightly deactivating, these are actually going to be ortho and para-directors. They are not meta-directors. These are ortho and para-directors. So this is our halogens. So now after our halogens are going to come our benzene. Our benzene, again, our generic benzene has no directing effects, right? Because the substituent, what is it? Well, it's just a normal hydrogen. This is our benzene here, so we can even write this out. This is the benzene. Now we move on to our strongly activating groups. So we have three that we'll look at here right now. Again, some of these are somewhat generic, so you can replace them with anything that sort of fits the category. But if we have a benzene with some R group, right, this could be a methyl, this could be a propyl group, this could be an isopropyl group, some R group attacked to our benzene, this is going to be strongly activating. Next, we can have, again, a benzene with some oxygen-containing substituent that also has an R group. And this R group, again, could be a hydrogen as well. So this could be an alcohol. So if we have a benzene with a hydroxyl group, well, that is strongly activating, meaning that it is going to be ortho-para-directing. So if we have an alcohol containing, or we have a hydroxyl group containing benzene ring, well, then if we undergo an EAS reaction, the product is going to have its substituent either on the ortho or the para positions. Now, finally, we have the strongest activating group here, which is going to be our benzene with some nitrogen-containing substituent. Specifically, it's some nitrogen bonded to two R groups, right? This could be something like an NH2. In fact, this NH2 is such a strong activating group that oftentimes we sort of have to undergo another reaction to sort of suppress the activating abilities of this NH2 so that we don't have a benzene that has a billion different substituents. If we want to attach only one substituent, say one bromine, that's not really going to be possible if we have NH2, right? If we have this NH2, a highly, like a strong activating group, well then if we undergo, say, bromination, we're going to end up with a bromine on each of these ortho and para positions. And so if we only wanted to attach one, we're going to have to actually suppress this. And we can do this by acylating this NH2, again, something we'll look at in the future. But just keep in mind that this NH2 is a very strong activator. So again, keeping it more generic, we're going to have our benzene with some NR2 group is going to be a very strong activator. So these three here, let me get rid of this bromine, sorry. These three here are going to be very strong. They're strongly activating. And what that means for us is that they're going to be ortho-para directors. Okay, so it's important that you sort of internalize this sort of flowchart where we go from our strongly deactivating to our halogens, which are slightly deactivated, but again, these are still ortho-para directors, all the way down here to our strongly activating ortho-para directing groups. So now that we have this in mind, again, why are things ortho-para directors? Why are things, para or meta directors? That's something that we'll look at in another video, kind of looking at the actual chemistry there. But for now, if you kind of just internalize this, we can work on some different problems that you'll often encounter on an exam. So let's say that we're trying to synthesize from our original benzene. We have a normal benzene here. And let's say we want to produce this as our product. We have a benzene with a chlorine and an SO3H. So what is the series of steps or a series of reactions that we must undergo on this benzene to create this desired product? And first look, again, if you weren't aware of ortho meta-para directors, you would think that there's two ways to do this, right? We could either first do some chlorination and then a sulfonation reaction to attach our SO3H group, or we could just start off with sulfonation and then do chlorination. So which is correct? Is it first we chlorinate and then we sulfonate? Or is it the other way around, where we can start off with sulfonation and then go on to our chlorination? Or are both of them correct? Would both of these work? Is one right and is one wrong? Well, let's take a look. Let's start off here with our sulfonation. Let's say we want to start with sulfonation, right? We want to take our reaction, or we want to take our benzene. Let's undergo sulfonation reaction. There was a video on this already. If you missed that, maybe again, take a look. Again, this video or these problems here are kind of assuming that you know different EAS reactions and ways we can add these different substituents. But anyway, so if we react with an SO3 in H2SO4, this is a 3, we're able to sulfonate this benzene, right? So we can put our SO3H here. So now, what about chlorination? We can chlorinate this, right, with Cl2. But now, what we need to keep in mind is where will this chlorine now attach, right? So if you remember from our sort of flowchart from earlier in this video, our chlorine is an ortho-para director. Again, this is a halogen. It's slightly deactivating, but it's still an ortho-para director. But our SO3H group here, this is strongly deactivating. If you can remember, this is a meta-director. So what does that mean? That means if we have this SO3H substituent on our benzene, the next EAS reaction is somewhat limited in that it can't attack anywhere that it wants. It can only end up attaching on the metacarbon. So that means that our product is going to look something like this, where we have our SO3H, but our chlorine is going to be on this carbon, on the metacarbon. So let's just draw this a bit nicer. But this chlorine is going to be on our metacarbon, right? This is our chlorine, and this is the SO3H. So there is a clear order of reactions that matters when we're doing these types of problems. We can't go in any order that we want, all the time, rather. So here we can see that one of them is a meta director and one of them is an ortho para director. And so we want to see what is it that we're trying to do. So when we approach these types of problems, what you want to first do is look at your substituents and see where they are relative to each other. So we say, hey, okay, these chlorine and SO3H groups are para to one another. Then you want to look at the directing effects of the substituents themselves. We can do kind of what we did here. We can say, hey, chlorine is an ortho para director. SO3H is a meta director. That means that if we want these substituents to be para to one another, we want to attach the substituent that is para directing first, right? So that means that we want to start with chlorination first. So if we take our benzene and we react with our Cl2 and FeCl3, we chlorinate this benzene, right? This chlorine is an ortho para director. So if we do our sulfonation next, we will actually get our desired product, right? We will now be able to attach this SO3H on the para position. So this is kind of the way that you want to think about these problems. All right, let's look at another example. Again, in the past videos, we looked at a couple EAS reactions. We've seen how we can chlorinate, we can nitrate, we can do other types of halogenation, we can do sulfonation, we can do our Friedel-Crafts acylation, Friedel-Crafts alkylation. There are a few other EAS reactions that I haven't made videos yet for, and again, I plan to do that in the future, but we may be using, I guess, different reactions that you haven't encountered in a future in a former video, kind of moving forward. So just keep that in mind. But let's start off with one that I guess we can do. We have seen this before. So let's say that we want to start off with, again, our benzene. And this is the desired product. All right, let's redraw this. Let's say we want to produce a product that looks something like this. We have a bromine. And here we have this sort of carbon chain on this position here. So how do we produce this product? How do we synthesize this from our starting material, which is our benzene? So take a minute, pause the video, and try to give this a shot. All right. So assuming that you tried this for yourself, but now let's get into what exactly we're trying to do here. Firstly, you can see that this is some sort of R group, right? If you remember from our flowchart before, this is an ortho para director. Our bromine, which is a halogen, is also an ortho para director. So how do we have two activating groups or two ortho para directors that are meta to one another, right? We can see that these two substituents are meta to one another. So how do we do this? Well, let's think back to the ways that we know to add sort of a carbon chain to a benzene. So far, we've looked at acylation as well as alkylation. These are two ways we've seen that we can attach sort of a carbon-containing chain to our benzene. You'll remember with acylation, we start off with an acid chloride, and we end up, effectively, as a generic reaction, we end up with something like this. And if you can remember, this is something that was a deactivating group, right? This carbonyl or this ketone-like product here, this is something that is strongly deactivating. That means we can use our acylation. And then how do we get rid of this oxygen here? How do we get rid of this oxygen? Well, if you remember, there are two different ways. We can do some sort of reduction reaction, whether we want to do Clemmensen or Wolff-Kishner reduction. We can then reduce this product to create, again, getting rid of this ketone and end up with something that looks like this, very much like what we want to do. So that's sort of a plan. That makes sense, right? We can start off with acylation. We can then brominate, right? This ketone is going to be a meta director. So before we reduce, again, that's why it's important, right? We want to acylate because we want to take advantage of the meta directing properties of this ketone group. If we have this ketone, we can have then the bromination. That way the bromine attaches on the meta position. And then we can go and reduce it to get rid of the oxygen. So that sounds like a plan to me. So let's see how that would work, right? We want to start off with our benzene. Let's start with the benzene here, which we first want to acylate. What are the two steps when we're looking at Friedel-Crafts acylation? It's very important that we number this effectively. So we start off reacting with an acid chloride, right? We want to react with an acid chloride. And this has to be in our AlCl3. Second, we want to react with water. So this is sort of the workup for Friedel-Crafts acylation. So what is our product going to look like? Well, we'll end up with something like this. Now what do we do? Well, this, we remember, is a meta director. Do we want to reduce this first? No, because if we reduce this, we end up with this. We want this as part of our product, but remember, we still have to brominate. If we do the reduction first and then we brominate, well, this substituent is activating. Remember, this is kind of what that generic R group looked like, right? So this would be an activator. This would be an ortho para director, meaning our bromine would not be able to attach onto this meta position. So we don't want to do the reduction first. So once we have this acylated benzene, what we want to do is then just go on with our bromination. So let's react with Br2 in FeBr3, which will allow us to attach our bromine on this meta position. And now, then, we can go on to do our reduction. So how can we reduce? Well, we can do either a Clemenson. So just as a quick recap, the Clemenson reduction is going to look something like this, where we have our zinc and mercury over HCl and ethanol. So this is the workup for Clemenson. And if we wanted to do Wolff-Kishner, I'll just abbreviate that WK. If we wanted to do Wolff-Kishner, that would be a little bit more elaborate, looking something kind of like this. And again, we want our KOH, and we want this all at 200 degrees Celsius. 200 degrees Celsius. This kind of all got cut out in the bottom. I can see that. So this is, let me rewrite that again, a bit smaller. Yes, we have a little more space, I think. Again, this is with KOH. Then all of this is at 200 degrees Celsius. Let's see, does that fit? Yeah, that should fit in the screen. So yeah, this is the workup for our Wolff-Kishner. So we can use either of these in order to, again, this is Wolff-Kishner. So we can use either of these to reduce this here. So let's just use our Clemenson for, the purpose of saving some space. Again, either of them would work, so it doesn't really matter. So if we react this, or rather we reduce this in ethanol, now we end up with our desired product. We have our bromine here, and we have reduced this ketone. So then there's a lot of somewhat thinking or planning that goes into this, where we think about what is it that we want in our product in terms of what substituents do we have, where are they, what are the different characteristics of these groups. So you have to keep all of these in mind when you're doing these types of problems. And yeah, I can make another video where we just go through a lot more problems like this. I think it would be very good practice. But that brings us to the end of this video. Hopefully it was helpful. If it was, please show your support by liking and subscribing. Leave in the comments any questions or suggestions for future videos you may have, and I'll see you in the next one.